This video will continue the concepts from 3.9. We'll continue looking into antiderivatives. The first video, we got through the basic idea that the antiderivative basically moves us in the opposite direction of the derivative. And there is a lot of sense how derivatives and antiderivatives cancel each other, but just to realize that we've already established that when we take an antiderivative without any additional information, all we can get is a general antiderivative. But any of the problems we did in the previous video, we were still kind of just floating trying to figure out antiderivatives, basically by doing some guess and check. Let's get some more concrete rules that we can follow. Now, I have to say, I'm going to do this by making an F prime chart. I believe that the best way to do this is to, again, always keep the ideas of derivatives and antiderivatives connected. And especially for those who go into Calc 2, I cannot emphasize that strongly enough. That when you are taking a derivative, you're just simply starting on the left side of this chart and moving to the right. And if you're taking an antiderivative, you're starting on the right side and moving to the left. Unfortunately, in my opinion, a lot of books make separate charts for derivatives and then separate charts for antiderivatives. And I believe thinking of these two concepts separately is a mistake. That we want to get used to seeing them as just in kind of an opposite order. So again, derivative left to right, antiderivative right to left. But let's, again, think about the rules for derivatives we have and realize what it leads to us with the ideas for antiderivatives. So starting here, if I had several functions, but that those functions are attached by either addition or subtraction, then that their derivatives would therefore be attached by addition or subtraction. So this leads to an antiderivative rule. And this is one I'm putting on the chart, but for a lot of people, it's just a simple enough concept that they could just remember it. So if I start with f plus or minus g here, that they're antiderivatives. I'll still take the antiderivatives of each of these separately, and that they'll still have the same plus-minus relationship. I mean, look at how this works, right? If I use this notation sliding over here, capital F prime plus or minus capital G prime, and that capital F prime and capital G prime are the same as little f and little g. So this was the derivative concept led to this, which therefore led to this antiderivative idea. Similarly, if I have a multiplier times a function, well, then when I take the derivative, that multiplier pushes along, and I take the derivative separately. And we do this all the time, right? 5x cubed has a derivative 5 times 3x squared. We're just accustomed to just taking the 5 times the 3 and making it 15. Same idea with the antiderivative. If in the derivative, this extra multiplier pushed along, the same thing happens in the antiderivative. So we'll just push that c along. Here's one that's a little new. We're used to having a plain old c or a plain old k here and having a derivative of 0. But let's just think practically, what if the derivative ends up with just a number? How do you take a derivative and end up with 5 or 12? Well, you must have started with a 5x or a 12x. So this line works pretty directly, that the derivative of kx is k, so the antiderivative of k is just kx. I don't need to change any of the notation. Remember, these really are saying the same thing. I just started with my regular derivative notation and then looked at it as my antiderivative notation. And that was the same thing here. Really the same. Derivative notation, and there's the antiderivative notation. But here, either way, that works the same. And here's the last one, everybody. We've already seen how common we use what we call the power rule for the derivatives. And I could try and force this to work the same way and treat these ends like the constants up here, but this comes up often enough, it's worth its own line. So if I start with an x to the n over here, we were kind of doing this through the examples, and if you go back and look at what we did, we looked at the antiderivative of x to the 5th, had an anti of 1/6 x to the 6th. The antiderivative of x squared was a 1/3 x cubed. So generically, look what's happening here. Starting with an exponent of n, our exponent becomes 1 bigger, so I get an exponent n plus 1, and then I get that same exponent, I get 1 over that out in front. So some people, as we said in the previous, they like to look at that as 1 over n plus 1, x to the n plus 1 power. Others prefer to write it as just one fraction instead of the 1 over out in front, just like we said here. X to the 6 over 6 is the same thing as 1/6 x to the 6th. That is huge, everyone. Again, power rule for derivatives we use all the time, and we're going to see the power rule for antiderivatives come up just as often. But, and there is a but here, the derivative power rule worked all the time. And as positive exponents, negative exponents, fractional exponents, that work cleanly. There's one exception. This still works if the exponent is negative or positive or fractional. So we'll see rewrites will still come up here. This only works if it's x to the n, one exponent, and that x is in the numerator. So we'll still see a lot of those rewrites that we needed for derivatives. We'll come up with, we'll still need to do those same things for antiderivatives. But one catch. Can you see an n value that would lead us into some trouble here? The catch is that this rule works for all n except -1. If you add x to the -1 and try to do this, you get x to the -1 plus 1 is x to the 0 and a 1 over 0 out in front. And that's goofed up for all kinds of reasons. 1 over 0 is going off to infinity, so you're getting infinity times x to the 0. X to the 0 is 1. And remember, everything we've said, how do you know your antiderivative is correct? It's correct if you can take the derivative and end up in the same spot. And that does not work here. X to the 0 is 1. The derivative of 1 is 0, not x to the -1. And that's a restriction we're going to be stuck with for the rest of this class. Even as some of you move into Calc 2, we're not going to get an answer for that until, I don't know, it's probably about a month into Calc 2 before you come back and see, well, what do you do if the exponent is -1? If this is a 1 over x, what is the correct antiderivative? Okay, so what we've really established so far are a lot of the basics. We still like addition subtraction so that we could take the antiderivative one piece at a time. Extra multipliers out in front just get pushed along. The antiderivative of k is kx. The antiderivative of a number by itself is that same number times x. And this general power rule antiderivative. The last thing I'm going to do, and instead of just making my chart going down further, I'm just going to make a second chart right here. We need the trig functions. And right now we're pretty limited, everybody. We can't put all the trig functions here and know all the antiderivatives. We can only start with the basic list of trig functions here and then use their antiderivatives appropriately. And way back, we talked about using u's instead of x's. I'm going to do that again. It's going to be a little bit, but at the end of chapter 4, you'll see why I keep stressing the letter u in this situation. So we know the derivatives. That sine of u has a derivative cosine of u du. Cosine of u, negative sine of u du for a derivative. Tan of u, secant squared u du. Cotangent of u, negative cosecant squared u du. And then the last two. Secant of u has derivative secant u, tan u du. And then cosecant of u, negative cosecant u, cotan u du. This especially, everybody, this is a big struggle for a lot of people who go into Calc 2 because, again, they memorize a separate antiderivative list. Realize, you know these derivatives, therefore you know these antiderivatives. And we're a little limited right now. We do not know the antiderivative of tangent. We do not know the antiderivative of secant. We need exactly these pieces. At this stage, this is how it'll work. We need exactly these pieces in order to know antiderivatives. So I know the antiderivative of plain old cosine is sine, but for plain old sine, that negative would have to come up over here. And again, we're still limited. Calc 2 will finish this off so that we would know the antiderivative of plane tangent, of plane cotangent, of plane secant, of plane cosecant. But for right now, this is what we're left with. So let's just have a bunch of problems that we're going to just say, find the general antiderivative. And as I kept trying to say, as we were making this list, we're going to basically do the same things we did with derivatives. We're never just going to dive right in. We're going to observe the situation, see what's good, what's bad, and then we'll act appropriately. Sometimes that'll mean just moving through the antiderivative one piece at a time. Sometimes that'll involve some rewrites. Notice there's no product or quotient rule, and there never will be, everyone. Antiderivatives start as this basic undoing of derivatives, but it's slightly misleading because we have these very nice concrete rules with derivatives. And for antiderivatives, especially those who go into Calc 2, you'll see a lot of this. We get general ideas, and it's basically we do what we can until we get something that works. But for right now, at least, we can point to some very clear-cut things. But to realize if there's multiplication or division, it's not like we're going to get to a product or quotient rule this semester. It's not going to happen. So we have to recognize that as trouble. Okay, so let's find general antiderivatives. So I'm not even going to label functions. I'm just going to give you a bunch of expressions, and that's where we start, and we'll take the anti. We could play the games that I'm giving you f prime and you're finding f, but really, again, just the general antiderivative. So let's find the general antiderivative for number 1 for the function x to the 5th minus 6x squared plus 10 minus sine x. So the first thing, I see 4 pieces. They're all separated by addition, subtraction. So I could just move and take the antiderivative one piece at a time. Right off the bat, the x to the 5th, that's my power rule. That's literally what I have on the side here. I add 1 to the exponent, I get a 6, and then I come out in front, a 1 over 6, or again, just divide by 6. I think more people prefer this, but again, I can't say it enough, everybody. If you would rather write it like this, there's no problem at all. Just a little more common, I think, to write it like that. Okay, but then right as I go into this next piece, this is not just an x squared, it's got the minus 6. So I know some of you can already start thinking about simplifying, but I'm going to be very literal. I'm going to push the minus 6 along, and then I'm working on the x squared. And I'm going to do the same thing for x squared that I did for x to the 5th. I add 1 to the exponent, and I get an x cubed, and I put a 1 over that new exponent out in front. And this 6 is still attached by multiplication. So it's minus 6 times 1/3 times x cubed. In a moment, just like we saw with derivatives, just getting the right answer is the first priority, but we do want to talk a little bit about cleanup. These will not always be, if this was like a 7 times 1/3, well, 7/3, that's as good as this gets, but this will become 6/3 that we can clean up a little bit. Okay, so I'll come back to that in a second. The plus 10 is plus 10x. This next piece, everybody, the trig functions, this is a spot where a lot of people are so reliant on the chart. You may have already spent a lot of time memorizing the derivatives, but especially in the beginning, trying to work backwards, especially with the negative signs. It is so easy to accidentally goof and just write minus cosine here, but that's not quite right, because the derivative of cosine is negative sine. With that extra negative, that would lead this to be a plus, but it's not. So that extra negative has to come up here. So for a lot of people, personally, I just really think about the functions to move backwards, and then I actually take the derivative. I really go back and think about that derivative and say to myself, okay, is it minus cosine or positive cosine? Well, positive cosine has the negative sign. That's the correct derivative, therefore this is the correct anti. If I had this as minus cosine, the derivative would be plus sine, and now it doesn't match. okay? And of course, the last thing, and as we're getting into the particulars, it's so easy to forget this, but every time you take an antiderivative, something comes at the end. At this stage, this general anti, we get the plus c. So this is a correct anti, and as I kept saying, that's just a personal preference here, which you'd rather see, but this. If we can clean up, we should consider it minus 6 over 3 is minus 2. So minus 2x cubed. And one more time, how do we know we're right? I could always take a derivative to verify. The derivative here, 6 times 1, 6 cancels, x to the 5th. The derivative here, don't even think about the derivative in the ugly form. Take advantage in the cleanup. And the minus 2x cubed has a derivative minus 6x squared. The plus 10x, plus 10. I mean, that's the kx rule, right? So that was a quick one to check. And as we kept saying, the derivative of plus cosine is minus sine. Every derivative matches here, so this must be the correct antiderivative. So that's problem number 1. Let's get several more here. Going to do several of these problems, and then I want to come back and finish this video with some quick reminders of how this connects back to position, velocity, and acceleration. Not to go too crazy with the word problems for now. And way back when I first introduced this, we talked about we would have a lot of different understandings of antiderivatives and integrals the same way we have derivatives. Right now, we're so focused on the technique itself, but later on, we'll get to this idea of area under the curve. That's the geometric understanding for the antiderivative, the same way that the derivative has the idea of the slope of the tangent line. And then in the word problem situations, we have that idea of rate of change for derivative. We'll get this idea of some sense of total. The total amount of work done, the total amount of miles traveled, the total amount of money spent, the total amount of water used. That will be the concept that'll go with the antiderivative with the integral. But again, that's jumping ahead. Let's really, really focus. This is very much like getting the shortcuts with derivatives. We're going to need these shortcuts for antis. So let's keep going. Let's go right into the next one. Let's find a general antiderivative for number 2. Let's look at the function. Let's go x cubed times 2x plus 7. And now we run into our first problem. The first of many problems, but this is just our first problem. This has multiplication, and that cannot be ignored. After we learn derivatives, we'd say, okay, I could use product rule. That might not be my best method. There might be an alternative. But once I see a multiplication problem, product rule becomes an option. But there is no product rule for antiderivatives. So I look at multiplication as a problem, and we're lucky enough that this is a problem we can fix. So my I should have wrote that in the previous to be clear. We're not getting a lot of notation at this stage. So just to make sure you realize this was the original and this is the anti, or fill in this is f prime and this is f, this is capital F. But again, trying to just get us to the technique. So this is still the original, and my equals, I'll just distribute that x. This will be a 2x to the 4th plus 7x cubed. And now just that little bit of multiplication, now I'm in a good spot. Now I've just got this simple addition. So now I could just take the antiderivative one piece at a time. The 2 pushes along. The anti of x to the 4th is 1/5 x to the 5th. Plus 7 pushes along. The anti of x cubed is 1/4 x to the 4th. And we're done, so we don't forget to put the plus c. And that is a good answer, but cleaning things up, and this is what I was trying to say here, we shouldn't expect that all these fractions are going to be perfect. I mean, 6 over 3 is great, that's 2. If it was 3 over 6, sure, reduce it to 1/2. But this is 2 times 1/5. 2/5 is really as good as we can make that. Or that alternative, 2x to the 5th over 5. Again, those are the two alternatives. No better or worse, they're just equivalents for each other. Similar here, 7/4 x to the 4th, or 7x to the 4th over 4. And either way, we finish with the plus c. So a good anti, and that is technically correct, but certainly our book is going to clean up and simplify and would show one of these two. Let's keep going. I'll flip back to this chart as necessary to remind you of, some of the trig functions and some of the other rules. But let's keep going. We're still finding the general antiderivative. And now problem number 3. Let's look at the function 10x to the 4th plus the cube root of x squared minus 7 over x cubed minus 12. Initially, this looks good. We still see addition, subtraction between terms, but what's not good? These two pieces. Radicals are exponents, but this also has another exponent. I can't deal with 2 exponents. I need to deal with 1. Over here, that has a setup where we might think about the power rule, but power rule only works when x is in the numerator. So once again, this is going to need a rewrite. And just like derivatives, maybe you just rewrite the pieces that need it. Maybe you rewrite everything, so that way it just makes it a little easier for you to move from left to right. Since this is the first one, I'll rewrite everything. I've got a 10x to the 4th. This will become x to the 2/3 power minus 7x to the negative 3. And the minus 12 is already in a good position. Now I'm in a nice spot. Now everything is ready to go. Antiderivative. Again, maybe you're already starting to see the cleanup. 10 times 1/5 x to the 5th. So that'll be 2x to the 5th. Again, I'm not trying to rush you, everybody, just like derivatives. It's great. It would be great if we could all jump and do that in one step, but there's never a shame in having 2 steps. 10 times 1/5 x to the 5th, then cleaning it up. We definitely want to see 10 over 5 reduces, though, right? That's certainly a nice cleanup, whether we are asked for that or not. But certainly, to get to here, that's a great thing. Here, just because this is a fractional exponent, so what? Now you're adding 1. 1 is 1 over 1. Common denominator, that'll be a 3 over 3. So I'll get 2 plus 3 over 3, 5/3. So I'll get x to the 5/3 power, and I get 1 over 5/3 out in front. And this is the first time we've seen this, so that's fine, but we don't often leave fractions like that. And regardless of whether you did it this way or like this, either way, you're looking at compound fractions. Clean them up. 1 over a fraction flips your fraction. So if I had not already cleaned that up, I would definitely do it now. This becomes 3/5 x to the 5/3. Here, the minus 7 pushes along. New exponent, you're adding 1, everybody. It's so easy. We get into the habit of now these exponents are getting bigger, and then people want to make this a -4, but the rule is to add 1. So -3 plus 1, we got a -2. I get a 1 over -2 out in front. This is all multiplication, so that becomes plus 7/2 x to the -2. Or that could certainly be 7 over 2x squared if you also wanted to move the exponent again, right? Put that x in the denominator to make that a positive exponent. Back here, and again, this is fine, but certainly as we've changed the cube root of x squared into x to the 2/3, we should be able to think backwards. This is the cube root of x to the 5th power. So again, little things that we could still keep going, but this is certainly a good spot. Not to forget, we still have one more piece. Minus 12 has an anti-minus 12x, and we get our plus c. Always, I can't say it enough. In the beginning, it's such a good habit. Take a derivative and then to take an antiderivative and then check your work by taking the derivative and seeing how these pieces match. Derivative here matches this. It's correct. Derivative here. And that's where taking this derivative is a bit messy. This is better. 5/3 out in front completely cancels with 3/5. There's your 1. Subtract 1 from the exponent. There's your 2/3. So you could always check these problems, and it's never a bad idea to think about that. Ideally, as we get further along, we should really only check if we're afraid maybe it was a little bit tougher, maybe it was something that just looks a little strange, so we want to double check. But it's something you could technically always do. Okay, but the last thing to realize, if you made a mistake with your rewrite in your original, you're not going to catch it here. If you wrote this as the 3/2 power, well, your antiderivative would match that, not match the original. So any rewrites, if we make mistakes there, we're not going to catch it by just testing our antiderivative and taking the derivative. So some good work here. Let's keep going, several more. Number 4, let's look at the function 3x to the 4th minus x squared. If we were taking a derivative, we would think about that as chain rule, but there is no chain rule either. We'll get something closer to chain rule at the end of chapter 4. That'll be the one higher level technique for antiderivatives that we learn. But again, we don't know it yet, and I can easily make up problems that you can't find antiderivatives for. So, but anything I do give you should work, will work with the tools that we have at our disposal. So what are we going to do here? Almost the same thing we did here. Look at this as multiplication, right? This is only squared, so write it out. 3x to the 4th minus x, 3x to the 4th minus x. This is still my original. Again, keep track of what you're up to. Multiplying this out, I get 9x to the 8th. I would get a minus 3x to the 5th, and then another one. That'll give me a minus 6x to the 5th plus x squared. And as soon as I clean that up, that was inner outer. I shifted it so it looks like multiplication, but now I actually multiplied. Now I can move into a nice clean antiderivative. Anti here, 9 times 1/9 x to the 9th is just x to the 9th. This minus 6 times 1/6 x to the 6th becomes minus x to the 6th. And then a 1/3 x cubed plus c. Okay, so I've tried to push us with a lot of the playing games. We've seen some of the basic rewrites. I mean, I could throw more. If we had division, we would have to divide it out. We would have no other option. So certainly, like I said at the beginning of this video, a lot of the same considerations that we made for derivatives have to be made for anti. But now let's get back to a few more of the trig functions. Let's realize, first off, that so much of the trig is again based off of this chart. So if we get nice pieces like this, they're already set to go. So if I had something like 4 cosine theta minus 6 secant squared theta minus 2 cosecant theta cotan theta, well, that looks messy. I mean, and this looks like it's got inner outer, and that looks like it has a multiplication problem. But the real point of finding an antiderivative is, do you know a function that has that as its derivative? And even though these look ugly and complicated, we know functions that have those as derivatives. Secant squared is on this chart. Antiderivative is tangent. Cosecant cotangent is on this chart. So we can get antiderivatives for each. So that's the first weird aspect of trig, but this one works out pretty nicely. What happens to the 4 here? Now I'm taking my anti. There was no rewrite here. Everything was ready to go. So the 4 pushes along, and the anti of cosine is sine. So I get 4 sine theta. And then similar, minus 6, and the anti of secant squared takes me right back to tangent. This one's a little screwy, because again, negative cosecant cotangent takes me back to cosecant. I need this negative. Or I push the -2 along, and then the anti of this as a positive would be negative cosecant u. The negative has to come up on one side or the other. So 2 little different ways to think about it, but either way will get us to plus 2 cosecant theta. And how do I know that's correct? Because of the derivative. All of these. The derivative of 4 sine is 4 cosine. Minus 6 tan is minus 6 secant squared. And plus 2 cosecant would become plus 2 times minus cosecant cotangent. There's the negative. And not to forget the plus c. So that looked ugly, and it's not that trig functions always just go by themselves. I mean, I did start you with one here that had a trig function mixed with other functions. But just as we're working, just to realize, that looked, again, kind of nice and kind of ugly at the same time, but everything here was actually friendly. So now, let's do one more trig. So we're on page 5 here, and we're still finding the general antiderivatives. We're up to problem number 6. And let's take a look at this one. Let's look at, how do we want to do this? Let's go sine squared theta plus cosine squared theta all over cosine squared theta. Initially, I mean, this just looks, oh, sorry, that was cosine squared. Sine squared plus cosine squared divided by cosine squared. Well, that's got a lot to it, and that's not on the f prime side of my chart. So this is gonna take some work. And, you know, we do a little bit of this in Calc 1. This comes up a lot more in Calc 2. The trig functions get their own special section reminding you of all the different identities and manipulations that come up. So, what can you do here? Well, we can't just take the antiderivative because there's just too much going on and it's not on our chart. And there's no good, quick way to break this down. I can't just look at this piece or this piece. I got all this mixed together. So, 2 good ways to work on this first one. Number 1, I mean, they both rely on identities, everyone. And this first one, sine squared plus cosine squared, I mean, that has to scream out to us that that is 1. That's the Pythagorean trig identity, sine squared plus cosine squared equals 1. So this is my original. I'm not taking an anti yet. I replace that with a clean 1. Is that better? Well, maybe, but maybe not, because I still don't have something on my chart. But if I take that one step further, 1 over cosine squared. Well, 1 over cosine is secant, so 1 over cosine squared is secant squared. Kept rewriting, working until I got something on my chart. And now finally I got something on my chart. All this just became secant squared, and the antiderivative of secant squared is tangent. Now, that's not the only way to do this. I recognize the identity right off the bat, and to be quite honest, everyone, if you see an identity, it's pretty likely that's going to be the key to simplifying in some way. But an alternative here, this is still the original. Some people might look at this and say, well, there's some division problem. This denominator is simple enough. What happens if I divide both? What happens if I try to actually divide and break it down? Well, this makes progress. Sine squared over tan squared, sine squared over cosine squared is tangent squared, plus cosine squared over cosine squared is 1. And then you might say, well, again, still not great. Tan squared is not over here either. But this is another identity. It's just not as commonly known. But tangent squared plus 1 is secant squared. It all comes from that Pythagorean identity, sine squared plus cosine squared equals 1. Take that, divide everything by cosine squared, and we get exactly this identity. Sine squared divided by cosine squared is tan squared. Cosine squared divided by cosine squared is 1. And then the 1 we used to get divided by cosine squared is secant squared. And now that's still my original. So no matter what, I manipulated in different ways, but in the end, I still ended up with the same good original function, one that I know a clean antiderivative. So either way, that is my final answer. Okay, now that's not the only thing that comes up. Certainly just to realize there's a lot of other possibilities here, but let's just take one last look. Number 7, let's look at 1 over 1 minus cosine squared. Still a tough one. Nothing jumps out initially. Again, we're trying to find the anti. It's not on my chart, so I've got to manipulate somehow. And here, we have to realize how often the Pythagorean theorem and the basic rewrites of sines and cosines into cosecants and secants is such a key here, okay? If you ended up with sine over cosine squared, we'll play with that. Sine over cosine squared can be sine over cosine times 1 over cosine, and you just change that into secant tangent. And that's something on on our chart, something on our f prime side that we know the original f. So, again, we could always work somehow, so we got to remember our trig facts. So in this one, I'm really using this identity again, but we're accustomed to sine squared plus cosine squared equals 1. Realize how you can manipulate that. If sine squared plus cosine squared equals 1, you could subtract sine squared from both sides, and cosine squared equals 1 minus sine squared. Or, and what's going to come up here, subtract the cosine squared from both sides, sine squared equals 1 minus cosine squared. That's what I'm seeing here. That's got to stand out. That becomes 1 over sine squared, which becomes cosecant squared. And one more time, that's on my chart. But negative cosecant squared takes me back to cotangent. So positive cosecant squared takes me back to negative cotangent plus c. Oops, one last thing I should mention while we're here. Let's just do a quick, easy one. Not focusing so much on the rewrites, but just the overall structure of what's happening here. What's the antiderivative of 4 sine theta minus 3? I don't need any rewrites here. I'm jumping right into the anti, and this comes in one of those little goofy situations. You actually get a minus 4 cosine, right? The anti of negative sine takes you to cosine, therefore positive sine takes you to negative cosine. The negative has to show up on one side or the other. So, or again, check with the derivative. The derivative of negative 4 cosine, negative 4 times negative sine, gives you the positive 4 sine. So that wasn't the point of this, it's this. Just to realize that we're so accustomed to using variable x. So many people do this part right and then put minus 3x plus c, but now you just change variables. That's the issue. If the variable was theta here, the variable's got to be theta here. So that's all it is. That would just be a minus 3 theta, not a minus 3x. But the other two parts are correct. Last thing, last idea from this video, everybody. Back to the relationship between position, velocity, and acceleration. That derivatives move us down the chain so that s prime is v, s double prime or v prime is a, and antiderivatives will move us back up the chain. So there's a couple little problems. They give you something like, given v of t is t cubed minus 6t, and s of 0 equals 3, find s of t. Do we realize that's the exact same problem we started with? That this is the derivative. So that's like saying, given f prime, find f. That's all we need to realize here, that with this relationship, v is s prime, so this is just an antiderivative. But in the same way, I get my 1/4 t to the 4th. I'm just going to clean this up. This will be a minus 3t squared plus c, and I'm still going to need this value to find c. Now, t is 0 and the whole function equals 3, and this is another one of those nice spots. Careful, everybody, cosine of 0 is not 0, but pretty much all your other functions, you plug in 0, you get 0. So 0 minus 0 plus c equals 3, c equals 3. So my position function would be this. We still have ideas for units that go along with this. There are some really neat problems in the homework that try and get you to do this and give you some real application situations. I believe there's one where they expect you to know the acceleration due to gravity. if you forget it or never knew it, if the acceleration due to gravity in metric units is negative 9.8 meters per second squared, if we're in American units, that would be negative 32 feet per second squared. I think there's one book in the problem that they try and get you to use this fact. Just one, though. Most of the others are just like this, trying to get us moving backwards. If I gave you A and wanted V, you'd do one antiderivative. If I gave you A and wanted S, you'd need two antiderivatives. Again, we did this earlier. If I gave you A and wanted S, that's just like the problem earlier where I gave you F double prime and asked you to get F. And the last thing I just want to say here, especially for those of you who might know a little physics or be interested in physics, this is where the kinematic equations comes from. So my last quick note I want to make here is just to realize that some of you may have seen this in some class, maybe high school or physics, but if acceleration is constant, which it is for anything that's thrown up in the air, right? Gravity is a constant acceleration that always pulls us down. So if you know acceleration is constant, then your A function is just an A value. I should be more specific. A of t equals A. The antiderivative, well, this is just a number, so you get AT plus C. And then if you realize plugging 0 in for t, the velocity at time 0 would be c. So a lot of physics people like to use this notation, v sub 0. The initial velocity plus the acceleration times t gives you the final velocity. By the way, even if acceleration wasn't constant, that idea is why both acceleration and velocity having the same sign leads to speeding up, or opposite signs slowing down. If your initial velocity is positive, but your acceleration is negative, t is always a positive number. This number is going to get smaller and smaller when you subtract from it, so your ultimate velocity is less than what you started with. But if this is positive and this is positive, then you're going to be adding to that value and get bigger. If this is negative and this is negative, well, again, when you multiply by a positive number, that'll stay negative, and then you'll just add the two negative values. So some people have seen this equation, a similar version. Final velocity is initial velocity plus AT. That's a little bit of a physics alternative. But one more antiderivative here gets us to position. This would have an anti-1/2 AT squared. Again, that's a number, so it's just pushing along. So that's really the variable. Add 1 of the exponent divided by the new exponent. That's a number. That's like a 10. So that'll have an antiderivative 10t. And then I'll get a new c. And that c, similar to this one, will end up being the initial position. And again, a lot of people have seen that in a physics class, and that was just given to you, but that equation is a direct derivation from calculus. So again, that's just purely for your interest, everybody. I think some people, enough people in Calc 1 also end up taking physics either before or after, so it's just something they've seen before. Problem number 60 in the book tries to get you to prove this yourself. So it's an interesting one. It's not a sign, but it's interesting to look at. But again, everybody, I'm perfectly happy as long as we remember this relationship. Just knowing the derivatives take us down the chain, so the antiderivatives would take us back up.